Hi everybody, welcome to another General Interest Sharcnet webinar. The topic today is dipping into C++17 parallel algorithms with Intel's Parallel SDL. My name is Armin Sobani and I'm with Sharcnet based on University of Ontario Institute of Technology. And this is my email address. So if there is a question after this talk, you can contact me directly. Okay, let's. The outline of today's seminar is first I try to have a really quick overview of the C++17 execution policies and to see what they are. And then I try to demonstrate how to use the Intel's Parallel STL library, which is one of the implementation that you can find to start using that feature. And at the end, we have a tutorial and also some benchmarks for exploring Parallel STL library on Sharcnet clusters. You can find the files for the tutorial section in the link below in the Git Sharcnet GitLab repository. You need your, I think you need your Sharcnet credentials to log into the GitLab server. So about the standard template library, any the C++ programmer knows what's the SDL. It's a standard library which is for more than I think 2 decades now, provides the standard containers and algorithms for programmers. It's the pretty much standard. It has a standard interface and influenced many parts of the C++ standard library. It consists of 4 components. There are containers that you put your data as different data structures in the containers. Then you use iterators to pass these data to algorithms, and these algorithms try to do some or change the data or other things. And there are also some functions that you can use for these algorithms, especially for those that accepting lambdas and also functors and also functions. The idea of having a parallel STL is really appealing. Because why? Because STL is familiar to most C++ programmers, and when you have a program that already uses STL containers and algorithms, if there is a possibility to use the parallel version, you can really easily do that with really minor changes to your source code. Currently, there are some the available implementation of C Parallel SDL. I put them in 2 categories. First is the C++ 11 parallel algorithms, which is now part of the core of the language, and it's the only compiler that supports it out of the box currently is Microsoft Visual Studio, starting 2017, starting version 15.5. But there is also Intel open source parallel STL that I'm going to address it today. Actually, yesterday I found that there is also another parallel library, HPX Stellar Group's HPX library, that in addition to other parallel things, it also provides an implementation of C++ 17 parallel algorithms, and the performance is not, if it is not better than Intel, it's on par. But it's not included in today's talk. There is also Kronos Group's Intel Parallel STL, which is based on the GPU, not CPU. There are also third-party C++ libraries, Boost Compute, which I talked about it in my previous webinar. You can find the video in our Sharcnet YouTube channel. There are also NVIDIA's Trust and AMD's Bolt, but most of these, in addition to CPU, they also support GPUs. But in today's talk, I'm just focusing on using Intel open source parallel STL to explore the parallel algorithms in C++ 17 standard. So what's the C++ 17 execution policy? For most algorithms, there is an, in C++ 17, there is an overload that accept, there are overloads actually, that accept execution policies as the first argument. Currently, there are 4. 3 of them are part of the C++ 17, sequential, unsequential, and parallel. And there is also, sorry, this one there is a problem of the copy paste. Actually, the unsec one is part of the C++ 20, and par and par unsec are part of the C++ 17. So you provide these execution policies as the first argument to the algorithm, and they act actually as a permissions, not an obligations. It means that the programmer says that this algorithm is good to be, for example, run in parallel, but it's a compiler decision actually. So maybe you use the parallel execution policy, but at the end it's not used. And based on the standard, they require at least forward iterators. So you can provide, for example, both vectors, which are random access iterators, but also support forward iteration, and also lists, for example. But some implementations, for example, Intel, they may have other restrictions. For example, for Intel Parallel SDL, it actually only supports random access iterators. So you can only use it on vectors and not on lists. This is an overview of all current standard template library algorithms sorted alphabetically. For some of them, there is no execution policy. For example, accumulate, there is no parallel version, or the version that accepts as the execution policy as the first argument. Why? Because there is another one, which I showed highlighted in the next slide, but it's actually reduce. So if you want to use the parallel version, you should use reduce rather than accumulate. And there are also exclusive scan, inclusive. Actually, this one is those that are not support execution policies. So binary search, equal range, OTA, and so on. Random shuffle, which is highlighted yellow here, is marked as deprecated after C++ 14. So it's not going to be available on C++ 17. But also there are some algorithms that they are parallel by nature. So there is no actually version that doesn't accept the execution policy as the first argument. These are exclusive scan, inclusive scan, reduce, and the other two versions of transfer, exclusive scan and transfer reduce. So how you can port to your current non-parallel algorithm to C++17 execution policy and enjoy the parallel version. The only changes that, for example, here is the sort example. This is the ordinary STL version that you just include vector and algorithm, then put some data in your vector, and then call sort using the iterators on your vector data. To make it parallel in C++17, you need only to add this include execution, and then add as the first argument this one, which can be one of the, here actually is correct, unsec is available after C++20, but actually one of the good thing about Intel Parallel STL is that it supports unsec right out of the box. So here, if you put std execution parallel, it tries to parallel the code if it can. But what's the difference between sequential and unsequential? If you provide unsequential, compiler tries to vectorize your loop or the algorithm using the SIMT or compiler intrinsics. So there are also, it's possible also to use both of them using parallel and unsequence policies if compiler actually can do that. So, but as I said, it's just the suggestion, and you just say that you like to do it like this, but it's the compiler decision at the end. But what's the Intel's Parallel SDL? Currently, the only compiler that supports C++17 out of the box is Microsoft Visual Studio, but it's only available on Windows platform. Intel, as the latest Intel C++ compiler release, which is 18.3, it supports, it actually included the Intel Parallel STL and also threading building block in the compiler. So you can use it right out of the box if you use the latest version of Intel compiler, but it's you need to use the not STL but PSTL, as we are going to see later. So if you want to experience with these parallel features in your current compiler, for example, if you use GCC or Clang, it's really easy to just download the Intel Parallel STL from the GitHub and start coding with that and explore all the things. That's actually the thing that we are going to do today. So Intel Parallel STL is on a header-only template library, which there is no need to link any libraries. You just include some header files. It's free and available on GitHub at the following URL. And it also depends on another Intel library, which is also available for free, which is Intel Threading Building Block. But Intel have offered to donate the implementation for GCC and Clang. So future version of GCC and Clang may actually use this implementation for the execution policy. So this is an overview of all parallel SDL algorithms here. Those that are in green, they support both parallel and unsequenced policies. Those that are in yellow, they only support parallel. And there are some algorithms like set difference and, for example, set union that they have execution policy as their argument, but it's the parallel version is not implemented in parallel STL, Intel's parallel STL. And those that are in blue, they are those algorithms that, as I mentioned previously, that they don't have a parallel version actually, so it's not in the parallel STL. So if you want to use the same sort example, this is the C++ 17 version. If you want to use the Intel Parallel STL for that, the difference is that you just add PSTL/ to these two, for example, headers. And rather than using STD for execution policy, you use PSTL. And they are exactly the same ones. But the good thing is that Intel also supports unsec execution policy, which is part of the C++ 20. And one thing that you should notice is that there is no need to change the STD before the algorithm, for example, sort to PSTL, only the execution policy. So what's the pros and cons about the Intel Parallel STL? As it provides, as I said, the C++ 20 unsec policy, and it has a good, strong scaling actually for parallel version. And another good thing is that it's a header-only library, so you just include the headers and start to enjoy the parallel version. But some of the disadvantages are it only works, as I said, with random access iterators. So you can use it mainly on, for example, vector and arrays, but you can use it, for example, on lists or forward iterator lists, other, for example, decks and those, or maps and other things. And actually also unordered containers that are introduced in C++ 11. And another problem with that is that it also relies on TBB library, so you need to also configure it. So in the next part, which is Parallel STL tutorial, I've actually made some of the benchmarks and made it available as a CMake build system on our GitLab repository, Sharcnet GitLab repository, that you can find it at the following address. So this is the web page for that. This is the URL, but maybe it's small in your screen, but you can find it in the slide. This is the whole instruction for this. You can see that actually I only added benchmarks for these 5 algorithms here, and these are the links to the complete description of these algorithms. For installing Intel Parallel STL, there are some dependencies, as I said. You need Intel Threading Building Block 2019 version, Parallel STL, and for these benchmarks, I also used Google Benchmark Library. The Intel Threading Building Blocks actually exist as a module on the Compute Canada systems, both Graham and Cedar, but we try to use Conan C and C++ package manager to install all these dependencies in our or your local home directory. The good thing is that when we use that, if we try to use different compilers, for example, Clang or Intel or GCC, it can be all of these dependencies can be compiled in your home directory and they will be available. But for installing Conan, you need the working Python environment. If you don't have a virtual environment in your Graham or Cedar home directory, you can easily do that using these commands, or you can find detailed instructions at this link. So the first thing is you need is to load a Python module and then make a virtual environment and activate it, and then upgrade the pip, and then the next step is pip install Conan. The next thing that you need to do is to add one remote repository that actually has the recipe for Google benchmark. And after doing that, then we can start to make the whole project using the CMake. So I'm trying to do that here right now. The only thing that you need is, I need to copy is this one, which is the actual repository. So usually it's better to use your Scratch file system to, for example, here I do that to do all these things. And I try to first clone. I use my Sharcnet credentials to do that. After doing this, you can have the whole thing in Parallel STL tutorial here. So the next thing is that to build, to make a, and also let me first make a directory. I make two directories, one build for GCC and one for Intel, to have both versions compiled and ready. And then I try to activate my virtual environment that has my Python. And then I go to, first I go to GCC version, for example. Here, if you try to do it without any module, it uses the GCC 5 as if I do module list here. But it's better to use GCC 7, the latest one available on the module system. So I do module load GCC 730. And then I try to install the dependency using Conan. You use Conan install using the and there is one parameter. You say that build all the missing packages. So because I've already installed these packages and they are in my cache, it only happens like inside. But for your case, because at first time it may take a while to build all these three packages: TBB, Google Benchmark, and Parallel SDL. And after having this, I can use CMake to build the whole thing like this. So you can see the Intel compiler was detected, and open MPS, IMD, and all these things are checked because we need those libraries, and also pthread. And after having this, we can make it, and because there are only five, I can parallel it to 5. instances. So after having this, for example, if I want to run the sort benchmark, I do bin sort. So here you can see that Google benchmark tries to show the architecture that is running. It's a CPU, the frequency here, 3.2 gigahertz. And this one only shows the total number of CPUs in the, actually on this node, which is the login node. But it's not actually the one that are used. So if you submit your job using, for example, 16 threads, it only used that one. But it always shows this 32. It doesn't mean that it's using the 32 cores for that. So as I recommended in the website, in the README, GitLab, it's better to, if you want to actually run these benchmarks, it's better to submit them as a job, or you use the interactive session using the command for that, which is salloc. So because I've already run this, and I just wanted to show you the sample. I don't try to allocate a session here. There is a warning here you can see about the CPU scaling, because these Xeon the CPUs on the RAM support the CPU scaling. These kind of things can add some noise. But the good thing about the Google benchmark is that it tries to automatically increase the number of iterations. So that it do that until it has enough sample, it has enough runtime to be good. But you can disable this warning using some commands, but only on your system. Because it needs a super user privilege to do that. But for our case, it's not really important, because I actually increased the number of the cases to, for example, 10 million, as you can see here, to prevent this kind of noises. So you can try this for other algorithms, for example, transform here, and see the results. But by default, it uses the maximum number of cores available here. And you can see the results here for different ones. I show you these results of these benchmarks later. What I'm going to show you here is that you can, if you want to do the same thing by Intel compiler, the only thing that you need to do is to go back to, for example, build ICC and do the same thing. But now, first I module load Intel 2018. And another thing that I need is to also export CC to ICC, and also C++ to ICC. And then try to install the dependencies first. Conan install, and then build. Let me see. And doing the same thing like this. So you can see that now Intel is detected, and it's trying to do the whole thing using the Intel compiler. One more feature that I've also included in the CMake file is that by default, the CMake builds using the -03 optimization for both, for example, for all the compilers. But maybe you want to do architecture optimization, which makes your code only run on, for example, Graham or that node, but it increases the performance. If you want to do that, the only thing that you need is to do CMake, CCMake, and change this use optimize for architecture to on, and then configure and generate it again. Okay. Now, if you do CMake again, you can see that it's detected the Broadwell here CPU and the optimized compiler flag for that. And if you do make -J5, it tries to make the optimized version. For the Intel, as I'm going to express it later, I don't know why, but the loops are not vectorized using SIMD. I did all the different flags and those things, but I couldn't make it work, and so the on-sec performance may be hurt because of that. But I tried to use the Intel 2018 and also the TBB and Parallel STL included on that package, but I've got the same results. I don't know what's the problem, but that makes the ONSEC and ONSEC PAR policies not as good as, I don't know, maybe Visual Studio and on Windows platform. But I'm going to show you the results of the benchmark now. The basis for algorithm selection, I just selected sort because it's a really the widely used algorithm in most fields and most programs. Maybe you need to sort your data. And also I selected some functional programming algorithms, which is really common in data science, map, filter, and reduce versions of those algorithms that you can see also the, the emoji version of this map, filter, and reduce and how they do the things. So it's actually map, filter, and reduce in the, for example, in purely functional programming languages like Haskell, which is the name maybe is different, for example, fold. But in C++ and STL, these are the name of the algorithms. For map transform or transform reduce, which do the map and reduce together. Filter, which is remove if, and also reduce, which the non-parallel version is accumulate, but the parallel version in STL is reduce. So this is the results for the sort algorithm using both GCC and also Intel compiler. I used both the default -03 and also the optimized one for both GCC and ICC, and these are the results. This is the, because actually the ONSEC is not available for sort. You only see the sequence or sec and par results for the sort algorithm. This is and this is also the sort algorithm of STL without any TSTL one. So you can see the scaling is pretty much high. I don't know, for both GCC and Intel, I got a really good scaling for this beyond the number of cores. This is the sequential version, which is, it shows that the Intel version, because it's provided by Intel, is even the sequential version is more optimized than the STL version. The performance for both GCC and Intel is on par, and the scaling for GCC is 64 and ICC 70. But for transform, you can see that it's different. For example, for a sequential, using the Intel compiler, pretty much make it much faster, even for sequential. And but there is no much difference between sequential and unsequential for Intel compiler, and also GCC. So it shows that it's not really working for OnSec and par OnSec, but the parallel version is for GCC is about 25 times faster, and for ICC 15. And that's can be is understandable, because when you have more tuned code, for example, here for SEC, Intel compiler has a better performance, so it's harder to make it faster in parallel. So despite the fact that there were 32 cores used, it only 15 times and 25 times faster on GCC or ICC, but it's still good. For transform and radius, there is this one is kind of strange, because for GCC, switching to SEC version, which is using supposed to use SIMD version, it's but not optimized one. It actually increased the the time. But after switching to optimized version of GCC, it's going back. But the OnSec version is perform better than the sequential version. And parallel versions are also here, but the scaling is not as good as transform. It's about 6 for both GCC and ICC. For remove if, it's actually the only one that you can see that for Intel, the OnSec performance is better than the sequential version, but strangely enough, the sequential version of Intel is higher than the, for example, GCC. But the parallel performance is, for GCC and ICC is about 14 and 19 as here. But you can see the par OnSec on Intel also performs a little bit better than the parallel version only. And this is the results for radius algorithm here. So you can see that the Intel here the performs quite well with O3, but when we use the optimized version of the GCC and the thing that the unsequential version for both GCC and ICC are better than sequential. So, but the par OnSec is not better than the par. So Radius also can benefit from the unsequence policy for both GCC and actually for GCC, not Intel. For the Intel, the sequential and unsequential is the same. So more things that I'm going to do here is that adding benchmarks for all parallel STL algorithms rather than these 5 to have better understanding of which algorithms can benefit better from the OnSec and also parallel ones. I also intend to including a strong scaling charts and results for all the parallel STL algorithms. I actually run the things. I have the data, but I don't have time to generate all the charts. And the last thing that I'm going to include in this, in the tutorial phase is adding benchmarks for stellar groups HBX library to have some comparisons about that.